Chapter 14, Electromagnetic Induction. So let's start electromagnetic induction. So these are our learning objectives. Let's start with the introduction. So what is basically electromagnetism deals with? Electromagnetism deals with two things. First is electricity and magnetism in a single framework, which is known as electromagnetic force. So moving electric charges produces magnetic field, and moving magnetic field produces electric force. So this is the main thing about electromagnetism, that the moving electric charges produces magnetic force, and this magnetic force basically produce electric force. So the interplay of electric and magnetic force is the basics for electric motor, electric generator, and many other techniques. So this is all about the introduction of electromagnetism, in which moving electric charge produces a magnetic force, and moving magnets produces electric force respectively. So this is the general elaboration of electromagnetism. So first is, what is electromagnetic induction? Give us application, and what is induced EMF and induced current. So the phenomena in which the change in magnetic flux causes an induced EMF basically is known as electromagnetic induction. Change of magnetic flux means that the change of field lines with respect to my area, and this will induce an EMF, and this EMF, this basically process is known as electromagnetic induction. Okay, the basic requirement for electromagnetic induction is the change in magnetic flux that I described. So first, case one is when there is no relative motion between magnet and coil, then galvanometer shows no current. Okay, when there is no relative motion, when the bar magnet, this bar magnet, basically there's a magnet here. When a bar magnet is moved towards the coil, let us say it will move in this direction, the magnetic flux changes and a current is induced. So there is basically, when there is a motion, there is the induction of electric charge or electric current. So when the bar magnet is moved away from the coil, the magnetic flux changes and a current is induced in the opposite direction. So this is all about the induction when a current carrying or a magnet is moved in a field lines. So it will induce a current in the magnetic field. Now the next thing is flux linkage. So what is flux linkage? So the product of number of turns, let's say this is my coil. So each basically is, this is one turn, two, three, and four. So this means that the value of n equals to 4. And the coil of magnetic flux of the and the magnetic flux. First is n number of turns of the coil, and the second is magnetic flux. So the product of these two is known as flux linkages. So phenomena of magnetic induction can be demonstrating in another way, as we when the current carrying conductor is moved away or towards the stationary coil. So apply the same. The EMF basically and the current will persist in the coil as long as flux through the coil is changing. So this means that if the field lines or my magnet moves in a magnetic field, so it will generate EMF and current respectively. Now, second question is, state the Faraday's law. So what is Faraday's law? Faraday's law basically it states that it is stated that the magnitude of induced EMF is directly proportional to the rate of change of magnetic flux through the coil. Again, that the magnitude of induced EMF is this one, is the rate of change of magnetic flux. So rate of change of magnetic flux will be total change in magnetic flux divided by, that is rate is basically with respect to time. So this means that induced EMF is directly proportional to total number in change in magnetic flux. So it will be n, as is n and flux, so it will be n, and there is change with respect to flux because number of turns is always constant divided by delta time, change in time. So it will be changing the proportionality into constant, so it will be induced EMF is equals to k, that is constant, into n delta phi divided by delta t. Here we suppose that the value of k is 1, so it will be induced EMF and delta flux about delta t. So this is basically according to my Faraday's law of electromagnetic induction. Okay, now a changing magnetic field induces a electromagnetic force in a conductor. The electromagnetic force is produced to the rate of change of field. Okay, the induced, now second thing is Lenz's law. So what is basically Lenz's law? The induced EMF always opposes the change in flux. Okay, so this is just like the resistance. Okay, that it is the negative to the rate of change of field lines. Okay, or the flux. So the direction of field induced EMF is given by Lenz's law. So it is basically the negative of my Faraday's law. So this is expression of Faraday's law of, this is the expression of Faraday's law of electromagnetism. The negative sign shows that the direction of induced EMF is such that it opposes the change in flux. Now the applications of Faraday's law. Yes, so Faraday's law is seismometer. So seismometer is a device used for measurement and detection of earthquake. So this is the major where it is used. So initial type, there are two types of seismometer. Initial type, inertial type seismometer, and second is electromagnetic induction type. So the inertial type basically is based on Newton's first law. It consists of spring mass system and it records the vibration. And electromagnetic induction, this is a principle of electromagnetic induction in which it transforms received vibration energy into electrical voltage. Now the next is state length law. So the statement is the induced current will always flow in such a direction so as to oppose the cause which produces the current. Okay, so this is basically the opposition to the cause of the current. Okay, it is always the inverse to the direction of flow of current. The condition for its application is we can apply Lenz's law directly to the closed loop because it refers to induced current and not to induced EMF. However, if the loop is not closed, we imagine as if it is closed, and then from the direction of induced current, we can find the polarity of induced EMF. Okay. So this is basically explanation of the Lenz's law. Now Lenz's law and law of conservation of energy. This is basically deals with mm, when north pole of magnet is approaching the coil, the induced current flows in such a direction that left side of coil becomes north pole. As a result, the motion of magnet is opposed. The mechanical energy spent in overcoming overcoming this opposition is converted into electrical energy produced in coil. So therefore, Lenz's law is in accordance with law of conservation of energy. Okay, so remember it that this Lenz's law is in accordance with law of conservation of energy. Now, Fleming right hand rule. So, Fleming right hand rule is that to find the direction of induced EMF, the Fleming right hand rule can be used. So, when the conductor moves at a right angle to stationary magnetic field, then direction of induced current is from right to the left. If the motion of conductor is downward, then direction of induced EMF will be from left to right. Okay. So it is stated as stretch out forefinger, middle finger and thumb of your finger hand so that they are at right angle to each other. If if the four finger point in direction of magnetic field, then the thumb is in direction of the motion of the current thumb, and the middle finger will point in the direction of induced current. The middle finger basically is, uh, is the direction of the current. Four fingers basically point in the direction of magnetic field, and thumb basically is the direction of motion of conductors. Okay, so what is induced EMF? The EMF produced in a conductor by its changing magnetic flux is known as induced EMF. And dynamic induced EMF is EMF produced in a conductor by moving it across a stationary magnet. So this is known as induced EMF. Statically induced EMF is EMF produced in a conductor by moving a magnet across a stationary conductor. Okay. So next is motional EMF. So the EMF induced by the motion of the, this is known as motional EMF. So as according to the relation F equals to Q V, B Q is the charge, V is the voltage, and B is the magnetic field. So it will be written as we know that F equals to B with magnetic field, I is the intensity, or basically the field line's intensity. Uh, then L is the length. So as rate of work done is W equals to, we know that rate of work done W equals to FV. So we know that F equals to V. I is basically V is magnetic field, I is current, L is length into V. So it will be VI LV. Okay, and the rate of the production of electric energy is induced EMF into the current. Okay, so this is what now induced EMF will be equals to according to comparing both equations. So according to principle of conservation of energy, the rate of work done is equals to the rate of production of electrical charges. So I am comparing equation 1 and 2. So this will be, written as this one, comparing both. I will just will be cancel out. So my induced EMF will be BVL. Okay, so this is the BVL. Now, according to the motion, so this is the expression for motion EMF. For if the angle between V and P is theta, so it will be induced EMF will be VBL sine theta. So these are the MCQ types. So, okay. What is self-induced EMF? So the EMF induced in a coil due to change of its own magnetic flux. It is known as induced self-induced EMF. Okay. So what is self-inductance? The phenomena in which a changing current in a coil induces an EMF in itself is known as self-induction. So this is, and what is basically self-induction will be equals to this formula, that will be equals to uh, just give me 1 second, equals to negative L delta I divided by delta T. L equals to induced EMF divided by delta I divided by delta T. The self-inductance of a coil can be defined as the rate of induced EMF produced in a coil to the rate of change of current in the same coil. Okay, so this is the self-inductance. Unit of self-inductance is Henry. So you can see that what is Henry and how we can define it. Explain the phenomena of mutual induction. Mutual induction is what in which changing current in one coil induces an EMF in the other coil. So let us say I have two coils A and B. So if there is a changing current in coil A, then it will produce an EMF in coil B. Okay, so this is the about mutual induction. So mutual induction will be same, that change equals delta I divided by delta T, and here it will be M due to mutual induction. So M equals to induced EMF divided by delta I divided by delta T. So again, the unit is same. The unit is Henry. So this is all about what are eddy currents. So the current is induced in the iron core due to changing magnetic flux of iron core. This is known as eddy currents. So eddy currents are induced due to changing in magnetic flux of iron. So this will be due to respective force and heat also. Okay. So this is about the MCQs of the topic. Now, alternating current AC generator. The device which converts the mechanical energy into electrical or alternating current signal is known as current generator. So, the Faraday's law of electromagnetic induction is basically the basic principle of AC generator. So, when a coil is rotated in a magnetic field through some magnetic or mechanical means here, so it will produce magnetic flux to the coil, so EMF is induced in the coil. So an AC generator main consists of armature. Armature basically it consists number of coils C, D, E, F. So basically this is C, D, E, F mounted on an iron cylinder, then permanent magnet to provide magnetic field to armature. Slip rings. The two slip rings are used. Carbon brushes, mechanical sources. So, what is the working? Working is when the side CD moves upward, this side CD moves upward. Right hand rule shows that the direction of current in form C to D and E to F, thus the current enters at B1 and leaves at B2. After half revolution, later EFE will be in the positive previously occupied by CD, and this current will flow from point 1 to point 2. Okay, so it will be from C to D, E to F, then C to D, E to F respectively. Okay, now the relation for this is the maximum value of induced EMF is NWAP. N is the physical number of point, W is the angular velocity, A and B is the side. Okay, so it will be sine omega 2t. With respect to sides, it's basically 0 to t up to 45 degree, then so 0 to 90, 180, 270, and 360 respectively. AC motor basically it is also which converts electrical to mechanical, and the relation is basically it works on the same principle of electromagnetic induction. So it produces by torque equals to N number of the turns n I a b and cos of alpha. Okay, so the detail is the parts are stator. Stator basically is the stationary part of motor, and the stator consists of a group of individual electromagnetic arranged in such a way that they form a hollow cylinder with one pole of each magnetic facing towards the center of the group. It consists of the group of electromagnets arranged around the cylinder with the poles facing towards the stator pole. Now, next is rotor. So, what is rotor basically? Rotor is the rotating part of motor and is located inside the stator and is mounted on the motor shaft. The objective of these motor components is to make the rotor rotate, which in turn will rotate the motor shaft. Okay, that's basically stator. This part is and this is the rotor. Now, what is back EMF? So, a motor is just like a motor running in reverse. Okay, so when a coil of the motor rotates across the magnetic field by applied potential difference and EMF is induced in it. The induced EMF is in such a way that a direction to oppose the applied EMF. It is the reason that the induced EMF is known as back EMF of the motor. So these are the expressions for V equals to induced EMF plus IR. So these are the special cases and so also the detail. I will send all the details to you. What are transformers? So transformers is an electrical device which changes a given AC voltage into large or smaller AC voltage because they work on the mutual induction. The construction consists of two coils of copper which are mechanically linked to each other. There is primary coil and secondary coil. The prime basically the number of turns in the this is basically the relation transformer ratio that Vs that voltage in secondary divided by voltage in primary equals to number of turns in secondary divided by number of turns in primary. There are two types of transformers, step up and step down. If the voltage across secondary is greater than primary, it is step up, and if the voltage across the secondary is less, it is known as step down transformer. Okay. And the current relation is inverse. So Vs upon Vp equals to Ip upon Is. Okay. So the relation of voltage and number of coil is directly while the voltage relation of voltage and current is inversely proportional to each other. What are energy losses in transmission? First is flux leakage. So there is always some flux leakage, means that the flux of primary coil does not link to the secondary coil. This loss is due to either poor design of core or a gap in a core. It can be reduced by winding the primary and secondary coils one over the other. Copper wire loss. The energy is lost due to resistance of wire used for primary and secondary. Third is eddy current loss. The induced current has step up due to change in magnetic flux of iron core of transformer. So the induced EMF are set up in a direction perpendicular to flux so as to oppose the cause that produces them and are called eddy currents. So the eddy currents cause the energy loss in the core due to heat produced in it. Okay. So the fourth one is hysteresis loss. This loss is due to repeated magnetization and demagnetization of core due to flow of alternating current. Next is what is the efficiency? The efficiency is the ratio of output over input multiplied by 100. The efficiency of transformer can be improved by The core should be made of by soft iron so that the energy loss due to magnetization and demagnetization should be minimal. The core should be assembled from laminated sheets of materials to stop the eddy current. The primary and secondary coils should be kept in such a way that the flux coupling between them is maximum and reduce the flux losses, and the resistance of the primary and secondary coils should be minimal. So this is basically all about from today's lecture. Hopefully you enjoy it. This is the revision of this chapter. So this chapter basically deals with electromagnetic induction. So that's it from today's lecture.